This is Paul, and in this script I plan to do a pair of classic proofs of countability of infinite sets. Let's start with the set of ordered pairs of natural numbers. An example of such a pair is 3, 2. I'll set up the screen, set up to plot, and by the way, in these scripts you shouldn't feel responsible for the details of the R. All I'm trying to do is use the graphical capabilities of R to make certain proofs come to life for you in a way that's hard to do if they're presented on a blackboard. I'm going to talk about serial numbers. Serial numbers start at 1, go on through 2, 3, 4, 5, and so on. If you're manufacturing objects, the first one you manufacture gets serial number 1, the second one gets serial number 2, and so on. No serial number is ever used more than once, and in principle, if you keep manufacturing forever, every serial number eventually gets used. So the serial numbers can be thought of as a metaphor for one-to-one correspondence with the natural numbers. Here's a function. Don't worry about the details of how it works. That plots a pair of numbers on the screen. And now we will do our first pair, 1, 1, and we give it serial number 1. Now let me tell you what we don't do. We don't head across the top row doing 1, 2, 1, 3, 1, 4. If we did, we'd never get to the second row. We don't go down the first column either with 2, 1, 3, 1. If we did that, we'd never go to the second column. Instead, what we do is move through the diagram along diagonals. So the next two pairs to which we assign serial numbers are the ones where the elements total 3. Then we deal with the ones where the elements total 4. We deal with the ones where the elements total 5. And I think you can see what's going on. Every pair is going to get a serial number sooner or later, and every serial number will be used once and only once. We've set up an explicit correspondence between the serial numbers, the natural numbers shown in red, and the pairs of numbers shown in parentheses, and that means, according to the definition of set cardinality, that these two sets have the same size. When we do the same thing with rational numbers, life gets a little bit trickier because a fraction and a rational number are not quite the same thing. You could argue that 1/2 and 2/4 are different fractions, but they represent the same rational number. So we want to associate the positive rational numbers with fractions that are in lowest terms, and if we encounter a fraction that's not in lowest terms in doing our enumeration, we want to skip over it. Apart from that, everything is much the same. Across the top I have the numerator. On the left I have the denominator. I reset my serial number to 1, define a function that will put a fraction on the screen, and I start by plotting my first fraction, 1 over 1. That's the integer 1, but it's a perfectly good positive rational number. It gets serial number 1. Then the fractions where the numerator and denominator sum to 3 get serial numbers 2 and 3 respectively. On the next diagonal, life gets a little bit more complicated because when both the numerator and denominator are equal to 2, that's the same number as 1 over 1, so I have to skip over it. That doesn't happen on the diagonal where the sum of numerator and denominator is 5, but in the sum equals 6 diagonal, we have to skip over 2/4, 3/3, and 4 over 2. Anyway, you can see what's happened. We have assigned 17 serial numbers to 17 fractions, and it's obvious that as we proceed, we will assign a serial number to every fraction. So we will have established a one-to-one correspondence between the positive rational numbers and the natural numbers. That's precisely what it means to say that the positive rational numbers form a countably infinite set. And you will be surprised throughout the year to discover that there are many important proofs where the first step is begin by enumerating the rational numbers, or the positive rational numbers, or the rational numbers between 0 and 1.